Serena switch prediction algorithm and Python tool, predicting the potentiality of riboswitch performance through detailed analysis of echoes in the ensemble. All right, what is Serena? It's a research tool that is used to analyze the ensemble for a two-state switch currently, and it provides a single number that represents the ability of that switch, of that RNA to switch. It's more of a E, so it predicts more like how is this RNA accepting of being a switch, and it does this through calculations at 3 different temperatures, 36, 37, and 38, going along with my theory that you can kind of poke around at energies, and if it's stable across energies, then it'll be more stable in the real world. So it's currently trained on and optimized for the PNAS labs. Same state NG1 was my focus. Just kind of picked that one. I remember I looked at it. It had a lot of good separation of good and bad. Some of the other labs, there's a lot of designs that either it's like some labs were like extremely easy to get relatively, or some were extremely hard. This one seemed to have a good distribution that would actually make it informative. And so this is the next evolution and iteration of DPAT. This is what DPAT should have been. DPAT, truth be told, when I coded it up, I had just started my software engineering path about 10 years ago, and I didn't understand about optimization. And I was doing a lot of linear, a lot of bad programming methods. And it was unusable. So I had to do everything manually. And so some things got lost in the details. But this is it's named after one of my heroes, Serena Williams, for her fearless determination and skill. So how does it do it? Well, it takes marker theory analysis one step further. Marker theory was an earlier theory that I had that was used in the PNAS labs to generate the high scores that Sarah generated based on my analysis and instructions to Sarah of what to use for acceptance and for acceptance criteria. And so Serena takes us a step further and actually looks for now echoes in the entire ensemble. And it does this using suboptimal folding versus the dot plot. And I developed this as a way to test out my theory that a good switches in silico ensemble will indicate, you'll be able to see in that ensemble whether or not this RNA is accepting of it being a switch. And to do this, I had to develop, so I used 4 new metrics and algorithms that I developed. One of them was one I've been working on for the past 2-3 years, ensemble variation, and the rest local minima variation, weighted structures, and comparison structures. I developed recently over the past few months. I had some inspiration from a paper that Digital Embrace that Jill shared, trying to get us to find detectors for riboswitches. And I was like, wait, I can do that for switches. And so I did this instead, as I do my own thing often. What does the in silico calculations? Now I'm actually using 2 different energy models. I'm using for all the first state unbound modeling, I use NUPAC for the RNA tools with that, and I'm using the RNA 95 energy set. The reason I use RNA 95 versus the other ones is RNA 95 seems to be more permissive, and I found that using RNA 06 and 99 and other ones, there were a lot of designs that Eterna scored as really well, but it wouldn't fold them. But RNA 95 would always fold them, and it was very permissive in that designs. I would get higher scores with Serena in RNA 95 than I did with RNA 06 and 99, if I'm getting those right. And so the second state FMN bonding is all used is all using the FMN hack done by El Nando 888 way back when. And so I'm using the sub-op routine for that as well. And there are no energies needed in this. You can use energies, but that's only to add extra bonuses, kind of as a confirmation thing. But this, it's kind of crazy. We're talking about all through this eternacon about, not using energies a little bit and starting to go more in structures. And it's actually where I've been going lately. It's kind of an interesting coincidence. So what are these metrics? Ensemble variation is a unit of instantaneous variation that was inspired by Newpack's ensemble defect, but I found that Newpack's ensemble defect was insufficient and honestly badly implemented, from a statistical point of view, in that they, for Newpack's ensemble defect, they actually, this is actually on the next slide, I'll mention this, but I'll just continue this thought now, is that Newpack's ensemble defect actually looks at the entire ensemble all the way to 0 from MFE's kcal numbers to 0 kcal, and there's like tens of thousands, millions of structures in there. And so what you end up getting is this number that only tells you how much variation there is, heavily weighted towards almost non-usable numbers. It just gives you a really general number. So local minima variation actually is a metric that uses EV, that uses the EV algorithm, but it requires various flavors. And this was the first thing that was inspired by that paper that Digital Embrace had mentioned. And I'll go into more detail of what the flavors are and how it uses EV in the next slides. Then there's weighted structures, which is a single secondary structure that I use that represents all the structures for an energy range in an ensemble. So think of 10,000 structures that you have now compressed into a single structure, which is basically MEA, the maximum expected accuracy I have come to find out. And then you have comparison structures, which is a novel structural representation that allows you to compare and contrast two structures against a third, and provide a single human readable line that it's pretty interesting. So here, ensemble variation, I already mentioned that it was my answer to Newpack's ensemble defect not being sufficient, because it didn't accurately represent 1 to 2 kcal from MFE, where all the action is. And so I developed EV to give an instantaneous look at the stability at specific discrete energy points along the ensemble. And in Serena, I look at 0 to 7 kcal delta from the MFE going into the positive direction. And I theorize that this value is a representation of the stability of an RNA fold, and on average less than 10, somewhat stable, 10 to 15, slightly unstable, and greater than 15, you have a very unstable. That's just general numbers, pulled them out of my head, kind of thing. So, and it uses a reference secondary structure to compare against, and to if all of these alternate structures are the exact same structure as the reference structure, then it has 100% stability, and you'll have a score of 1. If it has 0 stability, then it has a score of 0. And the way that this can take about half an hour to run for a simple RNA sequence. And so in Python, I optimized it to spin up multiple threads. And on an 8th gen i5, I could turn a 30-minute to an hour analysis down to 2 minutes now. It's pretty quick. So local minima variation it's a number that represents how much variation you have, but in reference to a local minima that you're looking for. And the higher the local minima, the higher the LMB value, which is thus a higher EV value, though it indicates that there's a lack of a reference local minima in that structure that you're looking at, and the lower value indicates that you have that there's that whatever you're investigating in that structure is present in whatever other structure you're looking at. And so the flavors is based on what you're using as a reference. So LMVC, which is LMV comparison, is a weighted structure. You use the weighted structure you use the weighted structure for the unbound ensemble. LMVR is you use the first structure found in each subset of the ensemble as you go. So 1 kcal, so you look at the energy, you look at the ensemble from 0 to 1 kcal and say there's 10 structures in there. The very first structure is your reference. And then you look at 1 to 2 and there's 9 structures. The very first one is that reference. And so you're actually getting a relative, so the R stands for relative. So you're looking at the relative variation as you go. And then you have the LMVM, which uses the MFE structure as a reference, and that's the unbound. And that gives you comparison of how stable it is compared to the MFE. So and that number is used traditionally, and that's what I developed it around originally, was to tell you how stable the RNA is and if it's going to stay in whatever state that you decided to fold into. And so weighted structures, I've already gone into this a little bit. It's basically the same as MEA that Jonathan talked about yesterday. And what it does is it actually looks at each nucleotide position for every alternate structure and finds the most common binding for that nucleotide. And I have an algorithm that basically if a dot parentheses, like if a parenthesis or a dot is the same configuration 50% or more, then it will retain that. And so comparison structures represents the similarities and differences between when comparison, one secondary structure against 2 others. As I said, it's human readable, and a dash represents that it has both folded and unfolded structures, that nucleotide in that weighted structure only exhibits generally nucleotides from both folded and unfolded structures. And if it has an X, then it's only the bound structure, so that's the second state. If it's a pipe, then it's an unbound structure, and if it's a dot, then it's neither. And so here's some examples. This is a representation of a secondary structure. And so this is looking at 2 basic, how do I say this right? In essence here, I have compressed tens of thousands of sequences into 2 groups, compared them against a third one, and said that the group of structures that I called the unbound, these nucleotide positions generally have the unbound only, and these nucleotide structures generally have them bound. It'll be more clear in a moment. And so this all results. So you then get, so then you can then do analysis on this comparison structure. And that is what, so Serena does an analysis on the comparison structure and the LMV values. And you get all these fun things, which is both, you get a number for the number of bound nukes and the number of unbound, the number of both, the bound to unbound ratio, the both ratio, the ratio of the amount of bound nucleotides, that it's the increase from the previous group to the current group, and then the unbound drop from the previous group to the current drop. the ratio of both nucleotides to the total amount. So you get all these ratios, and it's just a mess of data, and this is what it looks like. And you get some readable human readable messages that pop out that tell you some information. Each time it makes a decision, it says, okay, yeah, I decided that this was a potentially high fold change. There was a bonus because it was in the range of on-off predictions. Your EV was a little bit, you had really good EV, so you're adding a bonus, and it was primed to a switch, so adding some more. And so this actually had a score of 13, which is extremely high, almost too high. And so this is just what the code looks like that I make some of these decisions. It's all, the limits are hard coded right now, but the next state of this is to turn this into machine learning is the next state. That's the ultimate goal of Sarah, is to be AI. Excessive structures. So this is where we get into the meat. This is where we start. I found that there were designs that Serena was saying were really good, but the scores were bad. And I noticed that they had really high structures. Originally, I had 7,500 as the max. 20,000 is what I'm playing with right now. This data set that I have right now is with the 7,500 that I'm showing you. This is a screenshot I took last night because I'm playing around with some stuff. Because this is still in development a little bit. And so this, when I get into the walkthrough analysis, you'll see why that excessive structures is such a big deal. So this is what one temperature will look like when it kicks out the results. And I highlighted these to show you green is good, red is bad. And so you have so your MFE, so -31 to -30 kcal is your MFE to 1 kcal delta. And you see that you actually have the unbound structure is predominant, which is what you expect because you're sitting unbound, you're in that shape. But then it predicts that when you hit 1 to 2 kcal, the ensemble is actually trending to contain mostly the binding configurations of the folded structure. And you see I have these here where I have the modifier. Each time it goes, okay, yeah, this is a good switch. This is a high folding switch. This is a really good switch. The 3 explanations mean really good. 3 ats means it's just good. And so each time it hits one, it adds. And so this is actually a very good switch. And so what Serena is doing, and so each of these lines is represented by these values here. And so you see how there's a bound-unbound ratio increase of 0 to a 9. And so Serena caught that and said, oh, wait, that is telling me that there's a huge shift as you walk through the energy, which is the dance that was mentioned earlier. I completely agree with that. I call it a transformation, kind of a transformation of a triangle, transformation of a structure as it travels along its energies. And so this is saying that once you get that MFE, that FMN molecule in there, and that MFN molecule will boost the energy. And now you have a shift in that energy, and now you're going to be living in this area versus this area in unbound. So now you have a good switch, and I have a good score. Low scoring switch, you don't have any of that here. There is no transitions. This is just a single. This isn't going to fold. This is not going to switch, and you see a low score. And I got these ones actually, I don't have the design numbers on here, but I'll show you it in the next slides. This is actually pulled from where this one actually had a low score from this actually matched a low score in the Eterna data, and this matched a high score in the Eterna data as well. So walk through analysis of same state NG1 using Serena. So I'm using only cluster sizes greater than 150 just to ensure that I have good data and I don't have any weird outliers that are, because RNA is weird, as we all know. And so you have from 30 to 70, you have this huge number of just really low scores. You just get pegged there. And then you have actually pretty good, this 100, your Serena score is actually higher than your scores for 0. So you actually have a good trend, but you have these outliers. And those outliers, let's keep an eye on those. We'll talk about those a little bit later. But you can see that there's nothing less than -10 up here, and you get all the way down to -250 in the 60s. Serena, now looking at the switch subscore, and you see that a switch subscore of 0, which is a 60 score, or a 30, super low scores. And as you increase in score, your Serena score increases. Once again, nothing less than 20 up high. Down here, -250. Outliers are still there. And now you're looking at FoldChange, and you see that FoldChange, there's nothing less than 0 up here. You have really low scores, really for a low FoldChange. And so I originally thought this was a FoldChange detector, is what I designed it as. But then I noticed that FoldChange it's not as good with FoldChange as it is other stuff. And so I started looking at some more filtering, and I was like, you know what? What if I look at this, if I take out a lot of variables, a lot of variations, like clean it up, and I go, okay, what is it only doing when it switches? So I'm filtering. The Eterna baseline score is 30, Eterna folding subscore is 30. So any changes are relative to the folding subscore now. And you see it has pretty much the same plot as the other ones, just less outliers, a little cleaner. But now, same with the subscore, but we're also zoomed out really far. If you look here, you can kind of see that there's actually quite a big delta there. So this is actually what it looks like. Threefold max signal. So a threefold signal increase. Serena has predicted that the best switches did the best, and the worst switches did the worst. And there's a 15, almost a 10-point spread between the highest score for a horrible design and the best. And I'm really proud of this. And now if you look at the number of alternate structures, you notice that the Eterna score is, you have a whole bunch of alternate structures for the scores between 30 and 70, because that's actually something that Serena keeps track of. And as I mentioned, alternate structures, I was penalizing those. So that is the reason for this, because I penalize those so much that it just pulls it down. Well, looking at now the number of alternate structures for the switch subscore, and you see that you don't have any good switches with alternate structures over 100,000, really. I mean, you have this little outlier there. No, that's still under 100,000. So I set 100,000 as my limit. If I do a fold and I hit 100,000, I bail. I don't do any more calculations. I go 60. I scored it. There's no need to do any more. 100,000. Don't even bother. And so, and now if you zoom in to where that 100,000 is your limit, basically, if I did 95,000 here, you see that you don't really have anything good above 15,000. And so that's originally when I was doing my original training, I trained it on a small sample set and I saw like 3,000 was like the best one. So I just doubled that to 7,000. I ran these plots a few days ago and I was like, oh, well, I need to change those things, but I had already done a lot of work. And so I'm, the thing is that each lab kind of has a different max of what too many structures is. But when you control for, when you just do the fold change, I mean, when you plot and control for the switch score, they look the same, but you also don't have very many high scores because those labs were so hard to do. And so I'm still working on collecting data on those ones. So here's a look at a performing switches. So this is, if this is looking at the Eterna score from 50 to a 70 only. And these are the two outliers that I kept on talking about, and we kept on popping up. And you can see that they actually have a 0 baseline score, a 30 folding score, and actually a really good switch score. Why is this? Why are these behaving the way they are? Well, Serena says high EV, and it's way too powerful of a switch. It does nothing but switch. It can't stay folded. It wants to do nothing but switch. And because it has a high EV, it's not going to stay folded. It's not going to be very stable. So it falls apart. And see, 14 is really high. And this is, so that was Janison Lee's design. And then Sarah, same thing, high EV. And if you look here, it's a heavy amount of bound nukes, just a lot, which, you know, and then you don't really, this is really extremely strong and it's a 13. So like, you know, you strong isn't necessarily bad. You can have a really strong switch and it be good. Just sometimes really strong can be bad. And I'm going to show you a design next that will show you what a really good design it looks like and show you why these are not the greatest. This is 100. This scored 100. EV is down to, in the 1 kcal group is 1. That means probably that from 0 to 1 kcal, it just had the MFE only there. And when you get up further, you get 4, 6, 8. Like you're still sub 10, even up to 20, like 1, 2, 3. Yeah, you're like 4 kcal delta, and you're still a low EV. So that's a very solid, stable structure. And you have these nice static stems. You have this nice transition here. You have these dynamic stems, and you're not overly signaling. And this is one of the things I was talking about, how like switches are really sensitive. And if you, I think, you know, you got to have this nice little happy area. I actually went really fast in this presentation. And so I have a GitHub repo that you can get this software at. It's a work in progress, pip installable. If you pull it, use the eternacon 2023 branch, you can play with it. It's definitely a work in progress. I'm working on some like unit tests and optimizing it and making it proper to submit to submit to PyPy. First, I have a dream of having it on PyPy for some reason. And that's my presentation. Actually went really quick.